Orbitals and energies. Each type of orbital has a characteristic shape. For s orbitals, with L equals 0, the shape is spherical. As the value of n increases, so does the energy of the orbital, and the radius of the orbital increases as well. These are graphs of the probability of finding the electron at a certain distance from the nucleus. One thing we notice is that there are distances on the graph at which the probability is 0. These are called nodes. There are no nodes for the 1s orbital, one node for the 2s orbital, and 2 nodes for the 3s orbital. This is a cutaway picture of the 3 orbitals in 3 dimensions. Notice that the nodes are at a particular distance from the nucleus. They are called radial nodes. In general, any orbital will have n-1 nodes, where n is the energy level. For s-type orbitals, all the nodes are radial nodes. For p-type orbitals, the value of L is 1. These orbitals have 2 lobes, regions where there is electron density, with a planar node between them. This is an angular node rather than a radial node. This is because the node is related to a direction or angle from the nucleus, rather than a distance from the nucleus. The number of angular, that is direction-related, nodes in the type of orbital is the same as the number value of the quantum number L. So s-type orbitals have no angular nodes and are therefore spherical. All other types of orbitals have at least one angular node. p-type orbitals have one, a plane perpendicular to the direction of the orbital. The d-type orbitals have 2 angular nodes. 4 of the 5 have 2 planes perpendicular to each other, which produces 4 lobes. The 5th has a donut around what looks like a p orbital. The 2 nodes can be thought of as cones, pointed in opposite directions, which meet at the nucleus. There are 2 styles of f-type orbitals. 4 of the f-type orbitals have 8 lobes with 3 nodal planes. The other 3 f-type orbitals look like a p orbital with 2 donuts. These have 2 cones and a plane for their angular nodes. Energies of orbitals. For any atom that has only 1 electron, all the orbitals in a given shell, that is, all that have the same value of the quantum number n, will have the same energy. For neutral atoms, this is only hydrogen, but the same is true for ions of other elements that have only 1 remaining electron. All the orbitals in a shell are said to be degenerate for these atoms. However, whenever an atom has more than 1 electron, the repulsion between the electrons affects the energies of the different subshells. This splits the subshells in a shell and gives them different energies. The subshells are no longer degenerate, but the individual orbitals within a subshell are still degenerate. Configurations and orbital diagrams. We can do a number of things to indicate where the electrons are in the orbitals in an atom. First, we can draw the orbital diagram. We use a box, or sometimes a line, to represent each orbital, and place a half arrow in the box for each electron present, one pointed up and the other pointed down, representing the spin of the electron. Hund's rule is that when orbitals are degenerate, the lowest energy state is the one with the electrons spread out as much as possible and with the same spin if possible. Orbital diagrams may be of only the last few subshells, or they may be of all the occupied subshells. In either case, they tend to take up a lot of space, and a simpler shorthand is useful. This shorthand is electron configurations. Configurations show the distribution of electrons within the atom and consist of a number which shows the energy level, a letter for the subshell, and a superscript to tell how many electrons are present. The number and the letter together are the symbol of a particular subshell. Electron configurations may be of several types. The three most common are the full configuration, in which all of the subshells and their occupancies are shown, the short or noble gas configuration, sometimes called the condensed configuration, in which the symbol of the nearest noble gas before the element is used to represent the portion of the configuration up through that noble gas, and the remaining subshells are shown with their occupancies, and the valence configuration, in which the population in the valence shell, that is the highest energy occupied shell, is shown. Let's illustrate with the example of tin, atomic number 50. The full configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p2. In the full configuration, the subshells are listed in order of their energies. If you add up the superscripts, the total is the number of electrons, 50. The short configuration begins with the noble gas krypton, which is at the end of the fourth row. This represents the part of the configuration through the 4p and has 36 electrons. The rest of the configuration contains 14 electrons and starts with the 5s. 5s2, 4d10, 5p2. Note that the last three subshells in these two forms of the configuration are identical. The Kr symbol represents everything from 1s through the 4p. The valence shell is the fifth shell, so the valence configuration shows only those subshells in the fifth shell, the 5s2 and the 5p2. The structure of the periodic table is helpful in indicating what the configuration should be. Since we fill the subshells in order of increasing energy, the row the element is in tells us what possible subshells are in the last group to be filled. So if the element is in row 3, the possible subshells are the 3s and 3p. While if it is in row 6, the 6s, 4f, 5d, and 6p are possible. The row number is also the number of the valence shell. In addition, the different regions of the table correspond to different types of subshells. So, for elements in the two columns on the left of the periodic table, called the S block, the last subshell being filled is the S subshell of the row the element is in. The elements in the 6 columns on the right, except helium, which belongs with the S block, are called the P block. For these elements, we end with a P subshell of the row the element is in. The 10 short columns in the middle of the table are the D block, and the configuration will end with a D subshell, one less than the row number. And the 2 rows at the bottom of the table are the F block, which ends with the F subshell 2 less than the row number. The number of the column in order tells us the number of electrons in the subshell. So for iron, in the 6th column of the D block, we know that we will end with 3d6. And for tellurium, in the 4th column of the P block, we know that we will end with 5p4. Knowing these relationships allows us to very quickly get to the configuration without all that counting.